This is going to be a vodcast on weak bases. So just to kind of review, some of the things you definitely should know before you start this vodcast is make sure you memorize your strong and weak acids. Your strong acids and your strong bases. Those are important to making sure you identify the different types that are out there. Make sure you know the pH and the pOH scales. So remember, pH scale goes from 0 through 14, with 7 being the neutral. And pOH is the opposite. Know how to calculate the pH of weak acid using the ICE method. So you should be familiar with how to ice something to find the pH of a weak acid. Okay, just to review some bases. According to the Arrhenius concept, a base is a substance that produces hydroxide ions. So it was one of the first ways of defining a base, and just an example of a base under the Arrhenius concept would be sodium hydroxide. Sodium hydroxide would produce an OH ion in solution. The Bronstein-Lowry model is a little bit different. Remember that we have to pay attention to a number of things. So for instance, I'll use NH3 as an example. So NH3 plus water produces, it would be NH4 ion plus OH. So theirs is a little bit different. So a Bronstein-Lowry model, a base is a proton acceptor. So since the NH3 accepted the proton from the water, this is going to be the base, this is going to be the acid, and in this definition, this is going to be the conjugate base, and this is going to be the conjugate acid. So Bronstein-Lowry model, a base is a proton acceptor. This accepted the proton from the water. Hydroxide of alkali metals are strong bases because they dissociate completely dissolved in water. So again, another example will be lithium hydroxide. And the hydroxides of alkaline earth metals are strong dibasic bases, but they do not dissolve very well in water. Okay, so just a little bit of a review on some of the ideas of bases that we covered before. Okay, here's a list of those strong bases you should be aware of, so make sure you have committed these to memory. Okay, identifying weak bases is a little more challenging. It is not something that's very common for you to see and understand right away. So whereas when you have a strong base, NaOH would be one. It's easy to identify because there's a hydroxide. The one that we went over was an exception, was ammonia, NH3. So here's NH3. These are some examples of weak bases. And there is definitely a trend that you can see and identify right away. And some of it is you have carbons, hydrogens, and nitrogens in it. It's really this nitrogen that makes this a base. These hydrogens that are attached to this nitrogen is what really makes this a base. So when this accepts a proton, this is going to be the conjugate acid, CH3NH3. This is just an example of methylamine. So by seeing a couple of these, you can definitely see a trend, and you can definitely point out that there's going to be a weak base. And more often than not, when you see an N in here with H's, it's going to most likely be a weak base. So it just takes a little while to kind of see them and point them out right away. So again, just to write it out, bases are proton acceptors, according to the Bronstein-Lowry model. And it is the lone pair on the nitrogen that accepts protons. So it's this guy is what really helps define it as a base. And when I say those lone pairs, it's these lone pairs. This hydrogen is going to go and match up with that lone pair. So here's a general expression for equilibrium expression for bases. You're going to have some sort of base plus water, and it's going to form the base plus the hydrogen because it just accepted a proton, and you're going to leave hydroxide ion in water. So what makes a base, it's not because of the base that's producing hydroxide ions. It's actually the water that's turning into hydroxides. The H from the water is being stripped off from the base, and that's what's really making the hydroxide ions in solution. It's not necessarily the base itself that's producing it. So it's a little bit different than acids. The general expression of an equilibrium expression for a base, when we call it Kb for base, BH, so again, it's products over reactants, the base, whatever hydrogen got attached to it, plus times hydroxide divided by the base. So the general expression of a base. So just the strength of bases obviously is the stronger the base are the ones that have the hydroxides in it. So bases with hydroxides are generally strong. Everything else is basically generally considered a weak base. That's why it's very important to memorize your list of strong bases, because if you don't see it on the strong base list, then it's probably going to be a weak base. The smaller the Kb, the weaker the base. So let's show the ones that we did from the previous table. So if you take a look here, we do have Ka values. Oops. Hold on one second. Okay, so if you notice here, we do have, Ka values. We have Kb values, and the larger the Kb value, the stronger the base. So what we mean by that is that this NH3 can grab the H off of water much better, or much easily, than something like pyridine over here. Pyridine cannot take off that H off of water as easily as NH3 has. So the larger the Kb value, the stronger the base, and the opposite, the smaller the Kb value, the weaker the base. Okay, so NH3 is definitely a weak base. It is not any of the strong bases that we had to memorize, so I'm definitely going to have to ice this. So NH3 plus water, and it's going to form an NH4 positive plus hydroxide. And I'm going to ice this. So my initial is 15 molar here, 15.0. This is going to start out with 0. This is going to start out with 0. I'm going to subtract x. And again, the water does not play any part in this. It's a liquid. This is going to be a plus x here and a plus x here. This is going to be a 15 minus x. Again, this is going to be x and x. So they gave me the Kb value, so I'm just going to go ahead and plug it into the equilibrium expression. So it's going to be 1.8 times 10 to the negative 5 equals x squared over 15 minus x. Oops, this is not right. Oops, there we go. Little big x. Okay, so I'm going to assume that 15 minus x is equivalent to about 15, because since my Kb value is a very small number, I can make this assumption. So really, I'm going to have 1.8 times 10 to the negative 5 equals x squared over 15. Okay, so in this case, I got to solve for x in this expression. So just to speed up this process, I'm going to solve for x. Okay, and I get x to be, we're in a little space here, x equals, I got 0.01643, I'm just going to write a couple more numbers, 168, there we go. So, I got a value for x, that's great, but since I assume I have to double check my 5% rule, so 0.01643,168, and we don't have to worry about sig figs yet until the end, divided by my initial amount times 100, and I'm going to get a very, very small number, 0. So definitely passes the 5% rule. I can make this assumption. I now know what x is. So now that I have x, I got to count my sig figs. So since my answer only has 3 sig figs here, I can only carry 3 sig figs. So that's my value of x. Oh, I'm sorry, there we go. Okay, but I'm not done yet. I'm going to erase some of this just so I can have a little more space. So give me 1 second. Okay. So now I know what my X is. That X means, so as a reminder, that X means that's my concentration of OH. But I asked for pH. So several ways you can answer this, but I'm just going to find the pOH, which I find the easiest, and just subtract from 14. So pH equals negative log of 0.0164, and we're going to get a value of, let me plug this in my calculator, I'm going to get an answer of 1.79. So 1.79, but that's pOH. So I got to subtract 14 minus that, 1.79. So 14 plus, and I'm going to get 12.21, and that's going to be my answer, 12.21. Oops, a little messy. Will be my example of calculating pH of a weak acid. Okay, so it's not much different from calculating the pH of weak acids. You just got to make sure you know how to set up your expression for a weak base, icing it, and make sure you realize what your value of X is when you get it finally, and you have to make some adjustments after asking for the pH of it. Okay, so let's try one example on your own. Okay, so here, calculate the pH of a 1 molar solution of methylamine, CH3NH2. Kb is given to you. So go ahead and click pause, try this out, and see how you do. Okay, so for this problem, to make sure you know how to answer it, first part is to set it up. So CH3, NH2, methylamine plus water produces a CH3NH3 ion, positive, because it took an H off the hydroxide. So make sure you write it correctly. And it produces a hydroxide ion. The initial is 1 molar, so I iced it. So the change is minus X plus X plus X. Equilibrium is going to be 1.0 minus X. X and X. Since they came into KB, I'm going to plug it in. 4.38 times 10 to the minus 4 equals X squared over 1.0 minus X. Again, I'm going to assume, oops, sensitive, 1.0 minus X is equivalent to just 1.0, because X will be very small from the KB value. So really I'm going to have 4.38 times 10 to the minus 4 equals X squared over 1. In this case, I'm just solving for X squared. Okay, I got X to be 0.0209. Okay, I got a nice X. I have to check 5% rule, but for the sake of time, I'm not going to do it. So make sure you check it. It will be within the 5% difference, so it'll pass. And since this, and don't forget, this X tells me the concentration of OH, not H. So I'm going to use the pOH method, so negative log of this number, so 0.0209, and we get, so pOH equals 1.70, sorry, 1.68, my bad. But then we gotta find pH. So 14 minus 1.68, and I'm gonna get 12.32. So that will be your answer. If you forget that your pOH, you're calculating pOH, and you get a pH of 1.68, but you're dealing with bases, there's definitely something wrong with that. Okay, there we go. Hope this helps.